Hello students, welcome to EPG Pathshala. I am Dr. P.K. Aluwalia from Physics Department, Himachal Pradesh University, Shimla. Today we are going to discuss about a module, Ensemble Theory, Classical Part 7, Equivalence of Ensembles and Fluctuations, under the paper Statistical Mechanics. After studying this module, you shall be able to see how various types of ensembles, which microcanonical, canonical, and grand canonical ensemble are equivalent. Statistically calculate fluctuations in canonical and grand canonical ensemble without invoking thermodynamics by calculating mean square fluctuation, that is, the ensemble average of x minus ensemble average of x whole square, also known as variance of a physical quantity x, which is a measure of spread or dispersion of probability distribution about the average value. Appreciate that a system in equilibrium keeps on going from one microstate to another without going very far, leading to very small fluctuations in close vicinity of equilibrium state. Calculate variance of physical quantities such as total energy and total number of particles in different ensembles and see that these lead to same result for relative fluctuations, establishing their equivalence. We will also try to establish the fact that in equilibrium statistical mechanics, fluctuations are so small that probability of observing any value other than mean value is very, very rare. And to know under what circumstances fluctuations become important. Further establish this equivalence of the ensembles by deriving Bose-Einstein, Fermi-Dirac, and Maxwell-Boltzmann distributions from microcanonical ensemble. Derive a generic equation of state for an ideal gas for each of the three statistics. This module has been developed for postgraduate level as per the following subtopics: equivalence of different ensembles, fluctuations in different ensembles, that is, fluctuations in canonical ensemble and fluctuations in grand canonical ensemble, importance of fluctuations, Bose-Einstein, Fermi-Dirac, and Maxwell-Boltzmann distribution from microcanonical ensemble, calculation of number of microstates in different statistics, calculation of most probable distribution in different statistics, entropy, and equation of state. In modules 12, 13, 14, and 15, we dwelt in detail about microcanonical, canonical, and grand canonical ensembles and laid down a systematic procedure to derive thermodynamic properties and applied these to study a variety of interesting physical macroscopic systems such as classical ideal gas. We also saw that how this procedure helps us to calculate average values of physical parameters of the studied macroscopic physical systems. The most interesting aspect of the study has been that these three different ensembles took us from completely isolated system to closed system to a completely open system, yet gave same expressions for entropy, free energy, and equation of state, for example, for our prototype system called classical ideal gas. In this module, we proceed to seek an explanation for this interesting convergence to the same results through three ensembles representing three different physical situations. We can also seek this equivalence by calculating variance or mean fluctuations of energy in the case of canonical ensemble and number of particles in the case of grand canonical ensemble from their respective mean values, leading to a result that relative fluctuations from the mean values are extremely small for macroscopic systems. We shall build on the general considerations about fluctuations which we had studied earlier in module 11. In the end, we shall also look at some examples where these may become important and should not be ignored. We further establish the equivalence of the three types of ensembles by deriving Fermi-Dirac, Bose-Einstein, and Maxwell distribution functions by using microcanonical ensemble to see whether we get the same result as we got for these distributions by grand canonical ensemble. Equivalence of different ensembles. We approach this equivalence from point of view of fluctuations. Let us recall the results which we derived in module 14 on canonical ensemble for calculating average energy as given in table 1 and module 15 in grand canonical ensemble for calculating average energy and average number of particles given in table 2. Let us have a look at these tables. In canonical ensemble, we find when the partition function is summation over r e raised to power minus beta e r, average energy is equal to negative of the partial derivative of the log of partition function with respect to beta, which is equal to minus 1 upon partition function multiplied by partial derivative of partition function with respect to beta, which is equal to summation over r e raised to power minus beta e r divided by summation over r e raised to power minus beta e r. In grand canonical ensemble, where the equipotential was defined as equal to log of summation over s r e raised to power minus beta e s minus alpha n r, average energy is given by negative of the partial derivative of equipotential with respect to beta at constant b and constant fugacity, which is equal to summation over sr es e raised to power minus beta es minus alpha nr divided by summation over sr e raised to power minus beta es minus alpha nr, and average number of particles is equal to kbt multiplied by partial derivative of equipotential with respect to chemical potential at constant V and constant temperature, which is equal to summation over SR NR e raised to power minus beta ES minus alpha NR and summation over SR e raised to power minus beta ES minus alpha NR. Fluctuations in canonical ensemble. Relative root mean square fluctuation in energy in canonical ensemble. Equivalence of canonical ensemble with microcanonical ensemble. Let us take the derivative of average energy in canonical ensemble with respect to beta. That is, partial derivative of mean energy with respect to beta is equal to partial derivative of summation over r e raised to power minus beta er divided by summation over r e raised to power minus beta er with respect to beta, which is equal to negative of summation over r square e raised to power minus beta er divided by summation over r e raised to power minus beta er plus summation over r e raised to power minus beta er square divided by summation over r e raised to power minus beta er. The variance therefore can be written as the mean value of delta E square is equal to negative of the partial derivative of mean value of energy with respect to beta is equal to mean value of E square minus mean value of the square is equal to kbt square partial derivative of ER with respect to T, which is equal to kbt square CV. Let us now calculate relative root mean square fluctuation. This is given by the square of the mean of delta E divided by mean value of E, which is equal to square root of kbt square CV divided by mean value of E. Now, to estimate this relative root mean square fluctuation, let us recall for an ideal gas the mean value of E, which is equal to 3n kbt and CV is equal to 3n kb, where n is the number of particles in the system. Therefore, root mean square fluctuation, which was equal to square root of kbt square CV divided by mean value of E, becomes equal to square root of kbt square 3n kb divided by 3n kbt, which is of the order of 1 upon square root of n. Thus, relative root mean square fluctuation is of the order of 1 upon square root of n. For 1 mole of an ideal gas, number of particles N is of the order of 10 raised to the power 23. Hence, variance is of the order of 10 raised to the power minus 12 of the mean energy E, a very small spread about the mean energy, leading to an important conclusion that it is the same as we find in microcanonical ensemble. That is, the two ensembles give the same thermodynamical result. Fluctuations in grand canonical ensemble. Relative root mean square fluctuation in number of particles and energy in grand canonical ensemble. That is, equivalence of grand canonical ensemble with other ensembles. So let us first take relative root mean square fluctuation in number of particles. Let us take the derivative of average number of particles with respect to alpha, and noting that alpha is equal to minus mu upon kBt is equal to minus mu beta, we get partial derivative of average number of particles with respect to alpha is equal to partial derivative of summation over SR NR e raised to the power minus beta ES minus alpha NR divided by summation over SR e raised to the power minus beta ES minus alpha NR with respect to alpha is equal to minus of summation over SR NR square e raised to the power minus beta ES minus alpha NR divided by summation over SR e raised to the power minus beta S ES minus alpha NR plus summation over SR NR e raised to the power minus beta ES minus alpha NR square divided by summation over SR ES e raised to the power minus beta ES minus alpha NR whole square. Therefore, variation, or what we call variance in number of particles, which is equal to mean value of delta n square, is equal to partial derivative of the mean value of the number of particles with respect to alpha is equal to mean value of n square minus square of the mean value, which is equal to kBt partial derivative of n with respect to mu at constant t and v. Let us now calculate relative root mean square fluctuation, that is, square root of mean value of delta n square divided by the mean value of n, that is, the square root of variance divided by the mean value of n, which is equal to square root of kBt multiplied by partial derivative of n with respect to mu at constant t and v divided by the mean value of n. Now, to estimate this relative root mean square fluctuation, we can observe that in equation 6, numerator is of the order of square root of n and denominator of the order of n. The number of particles in the system, therefore, we have the square root of the variance divided by the mean value of number of particles, which is the relative root mean square fluctuation, equal to square root of kBt multiplied by partial derivative of n with respect to mu at constant t and v divided by mean value of n, approximately of the order of 1 upon square root of n. Stop 22. Thus, relative root mean square fluctuation is of the order of 1 upon square root of n. For 1 mole of an ideal gas, number of particles n is of the order of 10 raised to the power 23. Hence, variance is of the order of 10 raised to the power minus 12 of the mean number of particles n, a very small spread about the mean number of particles, leading to an important conclusion that it is the same as we find in microcanonical ensemble, that is, the two ensembles, the grand canonical and microcanonical, give the same thermodynamical result. We can also express equation 6 in terms of isothermal compressibility. Kappa T is equal to minus 1 upon V partial derivative of V with respect to P at constant temperature. Recall Gibbs-Duhem relation for a thermodynamic system, according to which number of particles multiplied by the differential of mu is equal to minus entropy multiplied by differential of temperature plus volume multiplied by differential of P. Therefore, partial derivative of mu with respect to n at constant T and V is equal to V upon n multiplied by partial derivative of P with respect to n at constant T and V. And partial derivative of mu with respect to V at constant T and n becomes equal to V upon n partial derivative of P with respect to V at constant T and constant n. Also, in terms of Helmholtz free energy F, dF is equal to minus S dt minus P dV plus mu dn. We have P is equal to minus delta F upon delta V at constant T and n, and mu is equal to partial derivative of Helmholtz free energy with respect to n at constant T and V. From 11th, it follows that partial derivative of P with respect to n at constant T and V is equal to negative of the partial derivative of F with respect to n and partial derivative of this with respect to V, and partial derivative of mu with respect to V at constant T and n is equal to the second order derivative of F with respect to V and n respectively. Therefore, partial derivative of P with respect to n is equal to negative of the partial derivative of mu with respect to V at constant T and n. Using equations 8 and 9 along with 13, we have partial derivative of mu with respect to n at constant T and V is equal to V upon n multiplied by partial derivative of P with respect to n at constant T and V is equal to minus V upon n multiplied by partial derivative of mu with respect to V, which is equal to minus V square upon n square multiplied by partial derivative of P with respect to V at constant T and n. Using 14 in 6, we have the relative mean square fluctuation in number of particles is equal to square root of kBt n square upon V minus 1 upon V partial derivative of V with respect to T at constant T and n divided by the mean value of n is equal to square root of kBt n square divided by V multiplied by the isothermal compressibility kappa T divided by mean value of n, which is equal to square root of kBt divided by V multiplied by isothermal compressibility kappa T. Relative root mean square fluctuation in energy. Let us take the derivative of average energy in grand canonical ensemble with respect to beta, and noting that alpha is equal to minus mu upon kBt, which is equal to minus mu beta. We have partial derivative of the mean value of energy with respect to beta is equal to partial derivative of summation over SR ES e raised to power minus beta ES minus alpha NR divided by summation over SR e raised to power minus beta ES minus alpha NR with respect to beta, which is equal to negative of summation over SR ES square e raised to power minus beta ES minus alpha NR divided by summation over SR e raised to power minus beta ES minus alpha NR plus summation over SR ES e raised to power minus beta ES minus alpha NR whole square divided by summation over SR e raised to power minus beta ES minus alpha NR whole square. So that variance in energy is given by the partial derivative of mean value of energy with respect to beta is equal to mean value of E square minus square of the mean value of energy is equal to kBt square multiplied by partial derivative of energy with respect to temperature at constant alpha and volume. Before we proceed further, let us carefully look at partial derivative of E with respect to T at constant alpha and constant V. Since n is not constant, its contribution should be there because of fluctuation in n. Therefore, it becomes partial derivative of E with respect to T at constant alpha and V is equal to partial derivative of E with respect to temperature at constant N and V plus partial derivative of E with respect to N at constant T and V multiplied by partial derivative of N with respect to T at constant alpha and V. Here, first term is the specific heat at constant volume CV as was in canonical ensemble, and the second term takes care of the particle number fluctuation. Recalling, mean value of energy is equal to negative of the partial derivative of the Q potential with respect to beta at constant V and alpha, and mean value of N is equal to kBT multiplied by partial derivative of Q potential with respect to mu, which is equal to minus partial derivative of Q potential with respect to alpha at constant V and T. We have partial derivative of energy with respect to alpha at constant V and T is equal to negative of the second derivative of the Q potential with respect to alpha and beta at constant V and F is equal to partial derivative of mean value with respect to alpha at constant V and T is equal to negative of the second order derivative of Q potential with respect to alpha and beta at constant V and F is equal to partial derivative of mean value of the number of particles with respect to beta at constant alpha and V. Noting that partial derivative of E with respect to alpha at constant V and T is equal to minus kBT multiplied by partial derivative of mean value of E with respect to mu at constant V and T, and partial derivative of mean value with respect to beta of the number of particles at constant alpha and V is equal to minus T square kB partial derivative of mean value of N with respect to temperature at constant mu and V. Equation 18 gives 1 upon T multiplied by partial derivative of mean value of E with respect to mu at constant V and T is equal to partial derivative of mean value of the number of particles with respect to temperature at constant mu and V. And equation 70 therefore becomes partial derivative of E with respect to T at constant alpha and V is equal to partial derivative of E with respect to T at constant N and V plus 1 upon T multiplied by partial derivative of E with respect to N at constant T and V multiplied by partial derivative of mean value of E with respect to mu at constant V and T. Putting 19 and 16, we get variance in E is equal to kBT square multiplied by partial derivative of E with respect to T at constant alpha and V is equal to kBT square into partial derivative of E with respect to temperature at constant N and B plus kB multiplied by T multiplied by partial derivative of E with respect to N at constant T and V multiplied by partial derivative of the mean value of energy with respect to chemical potential at constant V and T. Recalling, partial derivative of E with respect to T at constant N and V is equal to CV, and variance in number of particles is equal to kBT times partial derivative of N with respect to mu at constant T and V, which is equal to kBT multiplied by partial derivative of N with respect to E at constant T and V multiplied by partial derivative of E with respect to mu at constant T and V. Equation 20 can be written as variance in E is equal to kBT square, which is partial derivative of E with respect to T at constant alpha and V is equal to kBT square multiplied by specific heat at constant volume plus the square of the partial derivative of E with respect to N at constant T and V multiplied by variance in number of particles. Thus, relative fluctuation in energy in grand canonical ensemble becomes equal to square root of kBT square partial derivative of E with respect to T at constant alpha and V divided by 3n kBT plus kBT square CV plus partial derivative of E with respect to N at constant T and V square divided by 3 kBT multiplied by the relative fluctuation in energy in grand canonical ensemble becomes equal to square root of kBt square partial derivative of E with respect to t at constant alpha and b divided by 3n kBt plus square root of kBt square Cv plus partial derivative of E with respect to n at constant and Tv whole square divided by 3 kBt multiplied by relative fluctuation in number of particles. Importance of fluctuations. In this module, we had set upon establishing equivalence of three types of ensembles. We found that in each case, relative fluctuations vary as 1 upon square root of n, and for a macroscopic system in thermodynamic limit n approaches infinity, that is, relative fluctuations vanish. However, there are situations in which fluctuations can be very large and this result may not be true. This happens in the case of phase transitions where there are large fluctuations in number density equal to square root of Boltzmann constant multiplied by temperature divided by volume into isothermal compressibility. Because isothermal compressibility of the system there becomes exceptionally large. Critical opalescence is one such phenomena which happens near critical point in binary liquid mixtures when visible light gets scattered very strongly and clear mixture turns turbid. Bose-Einstein distribution, Fermi-Dirac distribution, and Maxwell-Boltzmann distributions from microcanonical ensemble. Now, to further see the equivalence between different ensembles, let us try to derive Bose-Einstein distribution and Fermi-Dirac distributions from microcanonical ensemble. We derived this result earlier in grand canonical ensemble. It shall be interesting to note that in spite of different surroundings provided to the system, the same results get reproduced. The system we have chosen is a gaseous system of fixed n number of particles which are indistinguishable and non-interacting and enclosed in a volume V with fixed total energy E. We also know that in thermodynamic limit in a macroscopic system, the single particle energy eigenvalues form a closely spaced set of energy levels. In this situation, one can divide the spectrum into a collection of cells, with each cell containing a cluster of levels, with each cluster I having an average energy epsilon I and an arbitrary number of energy levels Gi very much greater than 1. In a particular state of the system, first cluster may contain n1 number of particles and so on, such that the distribution set of particles Ni should satisfy the conditions as required by the microcanonical ensemble, that is, summation over I Ni is equal to n and summation over I Ni epsilon I is equal to E. Pictorially, situation is as shown in figure 1. For a particular set of values of number of particles, that is occupation number set Ni, distributed in a cell, the number of microstates is say omega Ni over that occupation number set, such that the total number of microstates omega as a function of total number of particles, total volume V and total energy E is given by omega as a function of n, V and E is equal to summation over that occupation number set Ni omega Ni. The omega Ni can be further expressed in terms of number of possible ways in which Ni particles can be distributed in each of the ith cells denoted by omega I, such that omega Ni in turn is equal to product over I of omega i's, where omega I depends on the type of particles, whether they are fermions or bosons or classical particles. Calculation of number of microstates in different statistics. Let us first take the case of bosons. In the case of bosons, in which any number of particles can be put in an energy level, problem is similar to putting Ni number of particles in Gi number of cells, which can be achieved by placing Ni number of particles in a straight line within two balls and permuting Gi minus 1 number of partitions to create Gi number of cells or energy levels. This amounts to shuffling Gi minus 1 number of partitions within the walls to enclose any number of particles in a cell. The total number of particles in partition walls is Ni plus Gi minus 1, and this can be achieved by placing Gi minus 1 number of partitions at any one of the locations Ni plus Gi minus 1. The number required is very easy to get, that is omega Be is equal to Ni plus Gi minus 1 factorial divided by Ni factorial multiplied by Gi minus 1 factorial. Thus, using equation 25, the total number of microstates for a given distribution omega over the occupation number set Ni is given by omega Be is equal to product over I on Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1 factorial. Let us now go to the case of fermions. In the case of fermions, Ni, the number of particles in the Gi number of energy levels or cells, is such that Ni is less than equal to Gi. Thus, omega on the Fermi distribution is the number of possible ways of arranging Ni particles in Gi states so that no more than one particle in each state is there, which is equal to number of ways of selecting Ni states out of Gi states. And this can be written as omega Fdi is equal to Gi factorial divided by Ni factorial multiplied by Gi minus Ni factorial. Thus, using equation 25, the total number of microstates for the given distribution omega over the occupation number set Ni is given by omega Fd is equal to product over I Gi factorial divided by Ni factorial multiplied by Gi minus Ni factorial. Now let us go to the Maxwell-Boltzmann case. In this case, particles are distinguishable so that any of the Ni particles may be put in Gi energy levels, leading to distinct states. So the first particle can be put in Gi ways, second particle can also be put in Gi ways, and so on, so that the number of distinct ways in putting Ni particles together in Gi states is Gi raised to power Ni. Furthermore, distribution set Ni can be obtained by selecting out of n number of total particles, n1 number of particles in the first cluster, n2 number of particles in the second cluster, and so on. This distribution itself can be obtained in n factorial over n1 factorial multiplied by n2 factorial multiplied by n3 factorial, and so on. Combining results 30 and 31, omega over the distribution set Ni for the Maxwell-Boltzmann distribution is equal to product over I n factorial Gi raised to power Ni divided by Ni factorial. However, this result needs to be corrected to take care of Gibbs paradox by dividing by n factorial factor. Thus, finally, the number of microstates in Maxwell-Boltzmann distribution is omega Maxwell-Boltzmann over the occupation number set Ni is equal to product over I Gi raised to power Ni divided by Ni factorial. Calculation of most probable distribution in different statistics. For each of the cases for the three statistics, we are now ready to go ahead and calculate using equations 27, 29 and 33 respectively for both Einstein statistics, Fermi-Dirac statistics and Maxwell-Boltzmann statistics respective distribution functions. One common link in each of the cases is that we are interested in the distribution which corresponds to maximum number of microstates omega given by equation 24. Since this corresponds to the most probable distribution, making entropy S of the system maximum. Since entropy is equal to Boltzmann constant multiplied by log of omega as a function of n, b and e, which in turn is equal to Boltzmann constant multiplied by log of summation over the distribution set ni omega ni. It implies maximizing log of summation over the distribution set ni omega ni. Here there is an important observation regarding this sum in the argument of log term, which is the fact that the sum over the distribution set ni on omega ni can be approximated by keeping only the largest term in the summation, provided ni and gi are large, that is, the term omega over that distribution set which maximizes it defines the most probable distribution, provided there is no violation of the constraints 20T and 23, keeping total energy and total number of particles fixed. So we can once again apply Lagrange's method of undetermined multipliers, so that condition for knowing the distribution set which maximizes this becomes delta of log of omega ni minus alpha multiplied by summation over I delta ni plus beta summation over I epsilon I delta ni is equal to 0, or delta log of product over I omega distribution ni minus alpha times sigma I delta ni plus beta times summation over I epsilon I delta ni is equal to 0. That is, delta of summation over I log of omega distribution over ni minus alpha of delta ni plus beta epsilon I delta ni is equal to 0. Now we are ready to use Stirling's approximation to write down for each of the statistics log of omega over a distribution ni. Case 1. Let us look at Bose-Einstein statistics. Summation over I log of omega Bose-Einstein as a function of ni is equal to summation over I log of ni plus gi minus 1 factorial divided by ni factorial multiplied by gi minus 1 factorial is equal to summation over I ni plus gi minus 1 multiplied by log of ni plus gi minus 1 minus ni multiplied by log of ni minus gi minus 1 log of gi minus 1, or for ni very much greater than 1 and gi very much greater than 1, summation over I log of omega over the Bose-Einstein distribution ni is equal to summation over I of ni log of 1 plus gi by ni plus gi times log of ni divided by gi plus 1. Let us find variation of 39 with respect to ni, that is, summation over I variation of log of omega be as a function of ni. This is equal to summation over I delta ni log of 1 plus gi by ni plus ni multiplied by 1 upon ni plus gi multiplied by delta ni minus ni multiplied by 1 upon ni into delta ni plus gi into 1 upon ni plus gi into delta ni is equal to summation over log of 1 plus gi upon ni multiplied by variation in ni. Case 2. Fermi-Dirac statistics. Summation over I log of W with respect to Fermi-Dirac statistics is equal to summation over I log of gi factorial divided by ni factorial into gi minus ni factorial, which is equal to summation over I gi log of gi minus ni log of ni minus gi minus ni log of gi minus ni, or summation over I log of w for Fermi-Dirac statistics is equal to summation over I ni log of gi by ni minus 1 minus gi log of 1 minus ni by gi. Let us find variation of 42 with respect to ni. This variation is equal to summation over I delta ni log of gi by ni minus 1 minus ni multiplied by 1 upon gi minus 1 into variation in ni plus ni multiplied by 1 upon ni delta ni plus gi multiplied by 1 upon gi minus ni variation in delta ni, which is equal to summation over I variation in ni multiplied by log of gi upon ni minus 1. Case 3. Maxwell-Boltzmann statistics. Summation over I log of omega over Maxwell-Boltzmann statistics is then equal to summation over I log of gi raised to power ni divided by ni factorial, which is equal to summation over I ni log of gi minus ni log of ni plus ni. Let us find variation of 44 with respect to ni. This variation is equal to summation over I delta ni log of gi minus delta ni log of ni minus ni multiplied by 1 upon ni variation in ni plus delta ni, which is equal to summation over I delta ni log of g by ni. Equation 40, 43 and 45, which we got respectively for Bose-Einstein distribution, Fermi-Dirac distribution and Maxwell-Boltzmann distribution, can be combined together in terms of a parameter eta such that variation in summation over I log of w over a distribution is equal to summation over I delta ni log of gi upon ni minus eta, where eta is equal to minus 1 for Bose-Einstein statistics, 1 for Fermi-Dirac statistics, and 0 for Maxwell-Boltzmann statistics. Substituting 46 in equation 71, we have summation over I log of gi by ni minus eta minus alpha plus beta epsilon I multiplied by variation in ni is equal to 0. Since all variations ni are independent, for equation to be true, the coefficients of each delta ni must vanish. That is, log of gi by ni minus eta minus alpha plus beta epsilon I must be equal to 0, which implies gi over ni is equal to e raised to power alpha plus beta epsilon I plus eta, or occupation number ni upon gi, the most probable number of particles in a single energy level, can be obtained as ni over gi is equal to 1 upon e raised to power alpha plus beta epsilon I plus eta. Entropy and equation of state. From equation 34, entropy can be written for all these cases by combining the following three results into a single result in terms of earlier defined parameter eta as summation over I log of omega eta ni is equal to summation over I ni log of minus eta plus gi by ni minus gi by eta log of minus eta ni by gi plus 1, so that entropy divided by Boltzmann constant is approximately equal to summation over I log of omega eta as a function of ni is equal to summation over I ni log of minus eta plus gi over ni minus gi over eta log of minus eta ni over gi plus 1. Using relation 51, we have S upon Kb approximately equal to summation over I Ni alpha plus beta epsilon I plus Gi by eta log of eta e raised to power minus alpha minus beta epsilon I plus 1. Using the constraints 22 and 23 for fixed number of total particles and fixed total energy, we can rewrite equation 53 as S upon Kb is equal to n times alpha plus beta E plus summation over I over plus Gi by eta log of eta e raised to power minus alpha minus beta epsilon I plus 1, or summation over I plus Gi by eta log of eta e raised to power minus alpha minus beta and epsilon I plus 1 is equal to S upon Kb minus n alpha plus beta E. Lagrange's undetermined multipliers alpha and beta can be interpreted as alpha is equal to minus mu upon kbt and beta is equal to 1 upon kbt. So that right hand side of equation 56 can be written as S upon kb plus n upon mu kbt minus E upon kbt is equal to G times G minus E minus Ts divided by kbt is equal to Pb by kbt, or Pb by kbt is equal to summation over I over Gi by eta log of eta into e raised to power minus alpha minus beta epsilon I plus 1. In Maxwell-Boltzmann case, eta approaches 0. Equation 59 gives ideal equation of state, that is Pv is equal to kbt summation over I Gi e raised to power minus alpha minus beta epsilon I is equal to kbt summation over I over Ni, which is equal to n kbt. It is interesting to note here that Gi, which is multiplicity or degeneracy of energy states, are so close that summation in equation 59 can be converted into an integration over momentum space, recalling that Gi is equal to 4 pi v p square dp upon h cube, so that pressure can be obtained as equal to 4 pi kbt divided by eta h cube integral from 0 to infinity log of eta e raised to power minus alpha minus beta epsilon p plus 1 p square dp. This can be integrated by parts to get 4 pi kbt divided by eta h cube multiplied by p cube by 3 log of eta e raised to power minus alpha minus beta epsilon p plus 1 limits going from 0 to infinity plus integral from 0 to infinity p cube by 3 eta e raised to power minus alpha minus beta epsilon p divided by eta e raised to power minus alpha minus beta epsilon p plus 1 multiplied by beta d epsilon p dp over dp. First term in 63 vanishes at both the limits, so that p is equal to 4 pi by 3h cube integral from 0 to infinity p square divided by eta plus e raised to power alpha plus beta epsilon p multiplied by p d epsilon p by dp over p. Recalling that total number of particles is equal to summation over I Ni is equal to summation over I Gi divided by e raised to power alpha plus beta epsilon I plus eta, which is equal to 4 pi v upon h cube integral from 0 to infinity p square over eta plus e raised to power alpha plus beta epsilon p dp is equal to integral from 0 to infinity 4 pi v upon h cube p square divided by eta plus e raised to power alpha plus beta epsilon p dp is equal to integral from 0 to infinity dn. Therefore, equation 64 can be written as p is equal to 1 upon 3v integral from 0 to infinity dn p d epsilon p divided by dp, or is equal to n upon 3v multiplied by p d epsilon p by dp. Noting that generally relation between epsilon and p is of the type epsilon is proportional to p raised to power r, p d epsilon p by dp is equal to r epsilon, and hence P becomes equal to R times N divided by 3V multiplied by the mean value of epsilon. For a classical ideal gas, mean value of epsilon is equal to 3 by 2 kBt and R is equal to 2. Therefore, PV is equal to N kBt, an ideal gas equation. Interestingly, this result applies to all the three statistics. So students, let us summarize what we have learnt in this module. In this module, we have learnt that microcanonical ensemble, canonical ensemble, and grand canonical ensemble, despite representing different surrounding conditions for the system, are equivalent. That the signatures of this equivalence at equilibrium lie in obtaining relative fluctuations of the same order, that is, of the order of 1 upon square root n for number of particles and energy in each of the ensemble. We also learned how to calculate the relative fluctuations in number of particles and energy in canonical and grand canonical ensembles, which are summarized in the table below. For canonical and grand canonical ensembles, second column corresponding to relative fluctuations in energy, and the third column corresponding to relative fluctuation in number of particles. That relative fluctuation in grand canonical ensemble has two parts, and the second part arising solely because of relative fluctuation in number of particles. That at equilibrium relative fluctuations from a macroscopic system from mean values are so small that one observes the mean values only. That at critical points, relative fluctuations in number of particles may be exceptionally large, leading to new phenomena such as critical opalescence in liquid mixtures. We also learned that three ensembles are equivalent in the sense that microcanonical ensemble also leads to same expressions of Bose-Einstein, Fermi-Dirac, and Maxwell-Boltzmann distribution functions as were obtained in earlier modules. We also learned how to apply the standard recipe of calculating number of microstates by actually counting these, followed by calculating the number of most probable microstates using variational method involving Lagrange's undetermined multipliers in the presence of constraints of microcanonical ensemble, obtaining occupation number for each of the three statistics with Bose-Einstein, Fermi-Dirac, and Maxwell-Boltzmann statistics. We also learned how to calculate number of microstates omega over a distribution set of particles Ni for each of the three statistics. The following table summarizes it respectively for Bose-Einstein, Fermi-Dirac, and Maxwell-Boltzmann statistics, where distribution set of particles is represented by Ni with energy level states set Gi. That the occupation number, which is number of particles per energy state for each of the states, can be obtained by applying method of Lagrange's undetermined multipliers, giving Ni upon Gi is equal to 1 upon e raised to power alpha plus beta epsilon I plus eta, where eta is equal to -1 for Bose-Einstein statistics, +1 for Fermi-Dirac statistics, and 0 for Maxwell-Boltzmann statistics, and alpha is equal to minus mu upon kBt and beta is equal to 1 upon kBt. We also learned to obtain equation of state of the system for each of the statistics. PV upon kBt is equal to sigma I over plus Gi upon eta log of eta e raised to power minus alpha minus beta epsilon I plus 1. We also learned to obtain equation of state independent of statistics by going from discrete representation to continuum representation in momentum space for a generic dependence of energy on momentum, with epsilon is proportional to p raised to power r, where r is equal to 2 for classical ideal gas and r is equal to 1 for ultra relativistic ideal gas, leading to p is equal to r multiplied by number of particles n divided by 3 multiplied by volume whole multiplied by the mean value of energy Thank you.